So let's start today's seminar. Today's speaker is Sungwoo from University of Chicago and fermionic. He'll talk.
Argon, actually.
Okay. He'll talk about the anomalies, TQFTs, confinement in Bosonic Chiral gauge theory.
Okay, thanks a lot. Thanks a lot for the invitation and introduction. So it's always great to visit kiosks, meet people, discuss people, and share what I've been thinking about recently. So today I will talk about a little bit of theoretical project that I worked on maybe 1 year ago, 2 years ago. The topic is to understand, take a strongly coupled field theory, meaning asymptotically free field theory, so it becomes strongly interacting the IR, and try to understand the possible phases in the infrared using some of the modern machineries, including generalized symmetries, fractional instantons, and some theorems regarding the existence or absence of a topological field theory that can possibly match some of the Hooft anomalies. Okay, so it has quite a bit of a moving part. As you see, the title is rather long. That means that there are many players coming together and providing as a whole set a non-trivial constraint in the possible phases of in the infrared. So one of the goals today I want to convey is that at least I want to make sense of what the title is or why we chose the title looks like this, okay? So I have to explain to you what I mean by new anomalies, new compared to what, right? And I would like to also talk about some topological field theories, and there are at least 3 different kinds, and why they play important role in understanding infrared phases. And what about the confinement, okay? So today, mostly, I want to say that the kind of theory we picked up, although it's not mathematical proof, it is unlikely that theory wants to confine in the infrared. So I want to show how they might be seen. Lastly, what does it mean to be bosonic chiral gauge theories? So I want to explain what I mean by bosonic chiral gauge theories. So we pick up a specific kind of field theory, which is a bosonic in the sense that I will explain. And then using these machineries, I want to say something about possibility of confinement or impossibility of confinement in the infrared, okay? So that is the goal. So what is the theory? So I want to now walk through you one by one. Oh, by the way, in any moment during the talk, my goal is not to bulldoze through everything we have thought through in the paper. It's a long paper, it's technical, there are many technical aspects of it. Some of them require some time to think through and understand. So my goal is not to explain every single one of them. Maybe I cannot do that within a single day or maybe a single talk. So feel free to interrupt, and I don't know like whether you had a time or chance to think about these type of topics that I will be talking about. So if something is not clear, you can ask me. I mean, I can give you sometimes technical answers. Sometimes I can give you more abstract version of answers so that you might be able to at least to get some sense what I'm actually talking about. Okay, good. So what is the theory? The theory, part number 1, I'm just going to talk about briefly what kind of theory I want to study. Okay. And then I will go through more details. The theory is I have some gauge field. So this is just like QCD type of gauge kinetic term. And then I will introduce 2 sets of fermions. One I call the psi, the other I call pi. Okay, and then as a formal machinery, I will introduce theta term 2. So in case you're not so familiar with the form notation, which I will use a lot today, because otherwise I have to put many indices everywhere. So this means the wedge product, it is antisymmetric combination of the 2 form, meaning it carries 2 indices. Whenever you see star, that means it's just a Lorentz contraction. Mu nu downstairs, mu nu upstairs. That's what it means. Okay. So I introduced 2 different kind of matter field, right? So here, psi transforms under color group, which I take to be SUN. So first of all, I take the SUN gauge theory to be concrete. And then, is blue visible, by the way, from the screen, or is it too difficult? Is that okay? Or I can use the different color. Actually, let me just switch to yellow. That I'm sure might be much more visible. So there's SUN gauge theory. And then psi matter field, the fermion, is an two-index symmetric representation, okay? And the chi transforms under conjugate of the two-index anti-symmetric representations. You might say, where did that come from? Why do you want to choose that? There are several technical reasons and theoretical reasons, as you will see. But for now, let me say that I want to study this. And let me just say that theta term, in principle, in the presence of massless chiral fermions, by which I mean there's a massless fermions who has chiral anomaly, is not physical. Okay, so as you may know, that's one of the solutions to the strong CP problem if you occurred were massless. So in principle, this is not physical, so I don't even have to introduce it, but it is so useful in understanding all the structure of anomalies. That's what I'm keeping here. Okay, so this is a theory. Now, I want to study asymptotically free theory, right? What that means is that this theory is very weakly coupled in the UV and becomes strongly coupled in the EIR. Okay, so
you're saying that the Hooft side, there is no mass term allowed.
yeah, so this is chiral fermion, so yeah, not mass term is allowed. Because I'm not adding a complex conjugate representation of this guy.
So it's just chiral.
This is chiral. This is purely chiral gauge
So
theory.
mass term is
It's not allowed.
forbidden because the side is either left or right handed, not because of the group, not because it's
Not because of the representation. There's that too, but this is only left-handed. So yes.
side and chi both are left handed in your.
Yeah, both are left-handed. Left-handed. That's right. Okay, so I should be.
Ask one more.
Yeah.
stupid question.
Yes,
why,
please.
Why do you?
Why do I study this?
The fundamental here.
Okay, good. So there are several reasons. Fundamentally, if you introduce, it will look more like QCD-like theories, right? So yeah, why don't you study that? So one of the
But we know that there are fundamental formulas in the nature. In nature,
That's right.
We don't know whether there is a higher representation or.
right. That's good. So here motivation is rather formal. Okay. So in other words, I'm not trying to solve a QCD. The motivation is that first of all, analyzing one theory to a complete level is almost impossible, very, very difficult, unless it is a very low dimensional field theories. And so the hope is that in 4 dimensions, if we can learn and understand better about any field theory, whichever kind, this is important and useful thing to understand. Another reason why I choose not the fundamental representations, but with at least a box more than 2 or equal to 2. And because technically, as I will explain, those theories enjoys more higher form symmetries, and those higher form symmetries provide extra constraint that possible allowed behavior in the infrared. Okay, so which I will explain. Okay, what these 2 boxes in principle lead to. Now, I need to make sure that the theory is free of gauge anomaly and asymptotically free, right? So gauge anomaly free condition, which means that I'm just looking at the loop of psi, and there's a 3 gauge boson, and then I'm looking at the loop of chi. I want to make sure that they sum up to 0, so there is no gauge anomaly, right? Okay, so that condition imposes some constraints. So this thing is basically number of species of psi times anomaly coefficient of this guy, which is a symmetric box, and then number of this guy and the anomaly coefficient that guy needs to be 0. Okay, and then this for SUN gauge theory is n plus 4, and this is minus n minus 4. Okay. So the cancellation that requires non-trivial constraint between the number of species. So one choice could be that I take this to be n minus 4 and n chi to be n plus 4. Of course, in order to be more efficient and economical, I can divide it by common divisor of these 2. So let me put some k. Okay. For example, if this is 4, this is 6, I can divide it by 2 without affecting this condition. Okay. So I'm just reducing number of fermions. Okay. So this is one condition. So this needs to be fixed. And like I said, I want to study asymptotically free theory. So it is strongly coupled in the infrared. That requires some constraint that from the beta function analysis. So that requires that this equation needs to be satisfied. Basically, total beta function is positive. Okay. So that means that you see, first of all, this theory does not admit large n limit. In other words, if you take a very large n limit, this becomes a king in the game, then you cannot satisfy this condition, right? So there's no large n limit. And after all, if you satisfy these two conditions, gauge anomaly free condition as well as the anomaly free condition, there's only a finite number of theories like satisfying this thing, okay? And then I wrote, any people from the Zoom can click the screen with the whiteboard in it, okay? And there are only finite number of theories satisfying this condition, okay? And as I will explain, most of these are bosonic, which I will explain, except 5, 6, 10. Everybody else is bosonic theories. And now you can come back to me on the board. In principle, you can hope to get the phase diagram, but in this case, n is not a continuous parameter, but there is going to be discrete lattice, and you hope to understand the phases of those theories. Okay. Today I will focus on one particular example, but a lot of techniques that I will talk about is applicable in general. Okay, now, what are the symmetries? So let me move on to the symmetries. Symmetries of this theory. So let me first discuss what I call naive symmetry. Naive symmetry means that if you wake up and somebody hands you this theory, you might write down this symmetry, but there's a subtlety. That's why I'm started calling a naive symmetry. Well, there is an m-psi species of fermion and there's n-chi species of fermion. So I should start with the SU m-psi cross SU n-chi. Okay, good start. Okay, hopefully you get there as far as you see this theory. Now, in principle, there is a two U1, right? So there is a U1 psi and U1 chi. Okay, but not both are. It is not possible that both are anomaly free, gauge anomaly free. What I mean by ABG anomaly free. So if you look at some U1 transformation and the fermion loop, and then you look at the color, okay, this is ABG anomaly, and which means that these two cannot be good quantum symmetry simultaneously. But there's a one linear combination which can be anomaly free and become good symmetry, and that is defined by the fact that the ABG anomaly coefficient is 0. Okay. So let me just do one exercise for you. What I mean by that. So there is let me choose this with the charge assignment that this guy has a charge q psi and chi has a charge q chi. Then ABG anomaly coefficient is there's a q, there's a u1 charge right here. So u1 psi, and then number of those guys. And then there is a 2 insertion of that thing that gives me Lincoln index. And then the same thing for the chi. So I want this to be 0. Then this is a good quantum symmetry. Okay, so that linear combination is a good U1 quantum symmetry. So you see that then, this is fixed by that condition. Then the charge assignment for this good symmetry is also fixed by this relationship. So one choice can be, for example, I can choose. Basically, I cancel this out. N chi, chi, and then I can choose chi to be n psi, psi. Once again, if this guy has a common divisor, I can divide by that, right? There's no reason to keep it large charge assignment. Okay, so here R is, for example, greatest common divisor of these two numbers. Okay, so there's a one good symmetry. So let me add this guy as a part of good symmetry. You can ask, okay, so here is a two-dimensional U1 system, right? There are two U1 directions. And then I said there's a one linear combination which is a good quantum symmetry because there's no ABG anomaly. What happened to the other direction? Okay, the other direction gives rise to some discrete symmetry because U1 cannot survive as good symmetry, but nonetheless, there can be subgroup of that U1 which survives to be good symmetry, which means that there is no ABG anomaly for that subgroup. Okay, so for now, let me just write that as some discrete symmetry along that direction, which is a discrete chiral symmetry along that direction. Okay, there's many discussion to be made, to be honest, about this. Okay, there's many subtleties, but let me move on with that for now. If there's any question, let me know.
This symmetry, global symmetry?
Yeah, so far I'm talking about global symmetry. Yes, that's right. This works really good. Yes. Good. So let me actually talk a little bit about it because I just throw that and then I didn't say anything. So let me take a little bit more responsibility. So in order to figure that out, let me consider direction where charge of these two guys is a 1 and 1. So in other words, I'm just looking at the U1 direction with the two same charges. So then theta parameter, which I just erased, beautiful, will shift. So in other words, action has I theta over 8 pi square trace F2. This theta parameter under this chiral rotation will shift. This, so by which I mean you can look at again that particular U1 direction, and then you look at the two color direction. Okay, so you look at the what is this shift? Theta will be shifted by, so I say 1 and 1. So 1 times n chi t chi plus 1 times n psi t psi, and then some U1 rotation parameter. Okay, that will be the shift of theta parameter. Now, which part survives to be good symmetry? Well, I'm allowed to shift the action by 2 pi integer times. So provided that this U1 parameter satisfies that this is equal to 2 pi times integer, that's a good symmetry. Okay? Because I'm shifting action by only 2 pi times integer. So that means that alpha of U1 e to the I alpha transformation satisfies 2 pi over n psi t psi plus n chi t chi. So that exactly looks like a discrete rotation with the rank of this thing, right? So that means that this U1 is broken by ABJ anomaly down to Z n psi t psi plus n chi t chi. Okay, so that's the sort of the example that I mentioned here. Okay. Now there's a side detail, like I said. So this so far straightforward. So far you can write this much. For example, this is a classic understanding of anomalies. But the truth is that some of these rotations, these discrete rotations I just analyzed, can be mimicked or can be done by some version of U1 transformation or some version of a Z m psi center rotation, some version of nz chi center rotation. There are abelian factors here. Some linear combination of those transformations can reproduce exactly the same transformation, which means that there's a redundancy in this transformation. I should not double count, right? Because not all of the ZP transformation are independent. I have to take into account those double counting issues. Okay, so that can be done systematically. But let me just quote the answer for you, because I can derive it, but it's gonna take another 10 minutes for that. Okay, so let me just write that. So taking into account correct redundancy shows the correct symmetry in this example, or actually, this is generally true, is the following thing. If you're curious, we have a rather long appendix deriving this result. Okay, so truly independent discrete symmetry chiral rotation is determined by this equation, which is great because now you see it doesn't require which charge direction I chose, because if you look at this, basically at least the number of counting of generators, there's only ZR discrete symmetry, and R is just this number. In other words, as soon as I specify my theory, R pops out as a single number, then I know there is a unique number of discrete rotation I can do in the theory. So this is discrete symmetry of the theory. I lied to you just now because that's a great start, because I just declared this is discrete symmetry, and then now I'm just gonna say that this may not be actual genuine discrete symmetry, because for this analysis, I didn't take into account possible redundancy from other abelian factors. I only take into account between these two. Okay, as the equation suggests. But that's detail. For now, you can just take that. Okay, so therefore, good symmetry is replace this with that equation. But that is the global symmetry, naive global symmetry. Okay, good. Now, there is some more symmetry. So let me just add it on.
So can I ask one question?
Yes.
Is this symmetry broken by the chiral condensate, or
very good? So that's what I will get to. So when I talk about the confinement, I will discuss whether this symmetry must be broken or should not be broken. If it is broken, how it should be broken, all that kind of business eventually. Yes,
Okay.
that is one of the central things.
And the discussion you did with the discrete subgroup right now, this also holds in case you have the symmetry broken. Is this completely independent?
You mean by chiral condensate?
Yes. I mean, if you go to the chiral condensate, you basically, with the condensate, choose a certain basis. And I right now can't see whether the discrete symmetry has some sort of alignment in this basis or whether the existence of the condensate makes a difference there.
Good. So very good. That's an excellent question, important question. So let me answer your question in 2 steps. What I'm doing right now is that given a UV theory, it's described by the Lagrangian, I'm just trying to figure out all possible symmetries of the theory. Okay.
Mm-hmm.
Next, what I'm going to do is that I will figure out all possible Hooft anomalies among those global symmetries. That's my next step. Once I do that, then I jump into the possible IR phases. What the IR phase must fulfill is that it must match entire set of Hooft anomalies, which I figured out in the UV theory. Now, discrete symmetry will be involved in the discussion of Hooft anomalies. In particular, those discrete or sometimes called the finite anomalies must also be matched. That's where the constraint about the possible condensate direction will be discussed. Some of the condensate will be ruled out simply because those condensate cannot match these discrete anomalies. In fact, instead of just choosing one particular condensate, I will show you how we can systematically map out entire space of chiral condensate. Okay, so that's where I'm heading for.
Thank you.
Yeah. Very good. Any other questions? Good. Okay, so there are a little bit of more symmetries, which let me just write it down. So in addition to this, again, this factor should be understood as more precisely this. There is some other symmetries. Okay, so for example, these flavor group include center, what's called the center symmetry. This is basically Zn psi chiral rotation or phase rotation acting on the psi. And this one will also include Zn chi phase rotation acting on fermionic chi. Okay, so that's called the center. And in addition to that, this theory has additional one-form symmetry. So this theory has one-form symmetry. So what is a one-form symmetry? One-form symmetry is a symmetry acting on a line instead of a point particle. And remember, this is global symmetry part, but secretly there is a SUN gauge group. So this one, in principle, can have a Wilson line, one-dimensional object. And because charged object is one-dimensional, it's called the one-form symmetry instead of a zero-form symmetry, which is regular symmetry. Now, where does this number come from? Well, remember, our fermion has our fermions are either symmetric or complex conjugation of the anti-symmetric. Now, if I had a fundamental representation, I can cut entire Wilson lines and screen away, which means that I can get rid of entire Wilson lines, which means that there's no charged object. That means that I should not have a symmetry, because how can I have a symmetry without having a charged object? But our theory doesn't have a fundamental symmetry, fundamental representation. Instead, the minimal thing has 2 boxes with it. What that means is that it can screen or cut the Wilson line if it had a charge 2 or more. So in other words, in the space of a Wilson line, charge 1, 2, 3, 4, 5, etc., our fermions are capable of get rid of, cut, screen all the even number charged guy. Okay? But it cannot screen the odd charged stuff. In fact, for example, charge 3 can be reduced down to 1 by getting rid of 2 factors of those charges. So that's where this thing comes from, in that, for example, if n were even, this becomes Z2 one-form symmetry, which means that there are only 2 kinds of Wilson lines. There's a trivial Wilson line and there is a Wilson line with a charge 1. And that's how I just explained physically why that is the correct one from symmetry. Okay? Anyway, so there's that symmetry. So this is naive symmetry, and I want to now talk about slightly more refined version of a correct structure of global symmetries, because that's crucial in figuring out the Hooft anomalies. Any questions? Okay, good. Right, now let me move on to, hopefully, the first one. So I just explained to you the theory. So let me keep this part. So there's that, global symmetry. Now I want to get rid of naive part. So how I might do that? So for this, I need to talk about what we call color flavor. I'm just writing very simple just because you want CFU fluxes that we found. So let me first tell you what is the general scheme, or what is the general plan here, game plan here. Okay, I want to maximize number of Hooft anomalies, right? Because the Hooft anomaly needs to be matched between UV and IR. The more I have in the UV, the more I must match in the IR. Therefore, I will get stronger constraint in the IR. Okay? How can I maximize number of Hooft anomalies? What are the Hooft anomalies? For example, let's look at the U1, for example, and then just this SU and M psi. The Hooft anomaly, for example, will look like U1 axial good global symmetry, and then SU and psi, SU and psi, right? These are global symmetries. So if I turn off entire background gauge field, this is 0. So it doesn't signal the inconsistency of theory, but nonetheless, theory knows about it if I turn on the background gauge field for global symmetries. Okay? And those behavior of theory must be matched. So here's one example of Hooft anomaly. Now, one then might wonder, what are the all possible background gauge field configuration one can possibly turn on? The more I have the kind of background gauge field I can turn on, I have more different kind of Hooft anomalies I can talk about. Okay? So here, the name of the game is that figure out all possible consistent background gauge field I can turn on for all entire global symmetry there. Okay? So that's the game. That's the flux part. So let me now technically explain. So even for this, I can already explain to you one thing. So instanton number, which described by this, so these two SU factor may look like hep-ph, right? So that's how the anomaly look like. You might wonder, what are the values this thing takes? If you don't do anything and they keep only SUM part, they take, normalized by A pi square, they take just the Z values, like 1, 2, 3, 4. Okay? Now, remember, anomaly of this guy in the presence of those background field might take something like I alpha E. So this is anomaly phase. Okay? Now, good. Now, suppose this is 2, for example. Then you see that this U1 should be broken down to Z2. Suppose you can even turn on 4. Then, okay, you have to broken down to Z4. So depending on the possible instant spectrum, you are changing the fate of symmetry in this way. Now, the important thing is that it is possible to turn on not only integer valued fluxes. If you are clever enough, you can even turn on Z and psi fluxes. In other words, now this is not 1, 2, 3, 4, but it's a 1 over M psi times integer. Because the fractional instanton is possible to turn on, but it's not like you can just turn it on and I say I want to keep this somehow. But you have to check whether turning those flux fractional instanton is consistent with the rest of the theory. Okay, so in other words, in more mathematical term, you have to ask what are the possible gauge bundle, principal bundle you can construct given a group structure. Okay, and depending on that, sometimes you can turn on, sometimes you cannot turn on. Now here, therefore, question is that given these global symmetries, now I pretend these are gauge symmetry, okay, because I just want to talk about background gauge field. So I pretend I gauged a little bit. I ask, what is the most general set of gauge bundle I can construct for this global symmetry? that will give me a spectrum of instanton that I can turn on. Therefore, a spectrum of Hooft anomalies I can talk about. So that's the goal. Now, there's a lot of discussion to be made about this. Okay, now let me get rid of this useless space. So let me talk about fractional instanton briefly. So I know if you haven't thought about this thing, it can be confusing concept. So just interrupt me, okay? So what is a fractional instanton? So let's first talk about SUN. So this n can be color part or m psi or m chi. Okay, this can be any of those. So for SUN gauge theory, so instanton factor or theta term, like I wrote earlier, looks like this. Okay, and for SUN gauge theory or SUN group bundle, this is integer valued, which is connected to what's known as a single index theorem. Now, I ask, can I study a theory which is like this? And turns out this has a more refined spectrum of instanton fluxes, or Hooft fluxes more precisely. Rather, this one has a z valued. This theory has a zn. This theory has a zn fluxes on top of integer valued ones. So you have a more spectrum of instanton fluxes or Hooft fluxes more precisely. So how do we construct that? So in order to do that, in order to construct such a theory, we start from so step number one. So start with SUN, but first you promote that to be SUN cross U1 and Zn, which is known as UN. So I want to first construct the U1 bundle, which is not like this, right? So I'm just telling you the roadmap. I'm just gonna first construct U1 bundle or U1 instanton spectrum. Then I will identify this guy with the Zn. So I just get rid of that direction. So then I will recover this theory, okay? And show explicitly that if I do that, indeed I will get 1 over n fractional instanton spectrum. And I will use that to talk about refined Hooft anomalies. How would I do that? So given this is a gauge field for SUN. And then this is the field strength of that thing. So I promote that to be UN. So yeah, I use notation of A hat. And the difference is that there's A, and then there's an extra U1 factor. So there's a U1 factor. So associated field strength will be, if you compute it, is this. Yes. Okay. Now, what I do is that in the action, let me check the time. Okay. So in the action, for example, this action now must include first this term. So I have to add this term to the theory, which I will explain momentarily. I just promote this to be this. There's a kinetic term, which I'm not writing. So why do I have to add this term? Okay, so starting from the SUN theory, if I want to do this, I need to add this term. Why is that? Because eventually I want to recover SUN with the proper modding structure. What that means is that this theory and that theory has the same number of local degrees of freedom. I'm not adding actual extra photon on top of SUN. So this thing makes sure that the trace of F2 is 0. So I'm projecting out this guy, local degree of freedom. Okay? So this is a Lagrange multiplier enforcing that condition. That's not enough though. So you might say this is good enough. Looks like I recovered SUN theory. That's not enough because my goal was not to go back to the SUN theory, but get back to this theory. In other words, if you compute the now Hooft flux or instanton spectrum you get just integer valued instead of 1/n valued. So in order to achieve that part, what we have to say is that we introduce or assumes that there is an extra symmetry to the theory. There is a warm form symmetry under which A1 hat transforms like this. Oops, sorry, not D. This is a one form. Gauge parameter is also one form instead of a function. So for zero form gauge transformation, you might see that this is a zero form, but now this is a one form. So that means that the field strength transforms like this. Okay, so let's postulate that I have imposed this extra symmetry. Then what happens? This is not invariant under this transformation, right? This is going to just shift. Kinetic term is not invariant. This is not invariant. So I screwed up. So I have to fix this thing. So in order to make sure that my theory does satisfy this one form symmetry, I have to introduce a two form gauge field, which I call B2. Under this transformation, B2 transforms as this. Sorry, just this. Yes.
Can you explain again what are little f and capital F and F hat and A, little a? And
Oh,
A
yeah, sorry, yes.
I lost totally.
Yeah, okay. A hat is the U1 gauge field. Okay. F2 hat is U1 field strength. F2 is a Lagrange multiplier introduced to enforce the fact that the trace is zero, so that I get rid of extra U1 degrees of freedom. If there's a trace, that means there's an extra degree of freedom, so I have to get rid of it. So that's why I introduced that. So far, that's all the only meaning of this term. Okay? Is that clear? Or
What are the hatted and unhatted?
good. So here, unhatted guy was for SUN. Hatted guy was for the UN. So first, operationally, I promote SUN theory to the UN theory, but yet I want to project it out the UN degree of freedom. So that's why I imposed this traceless condition. And then eventually, instead of going back to the SUN theory, I want to land it on this theory. In order to do that, this is not enough, and then I have to assume that there is a one form symmetry. And then I will show now that if I assume one form symmetry properly, indeed, I will go back to this theory. But again, the reason why I'm playing with all of this is to make sure that I have a most refined possible spectrum of Hooft fluxes, which will allow me to have a maximum number of Hooft anomalies, and therefore stronger constraint in the IR. Okay. All right. Good. So now let's see. So now let me see how I can make sure that my theory is invariant under this one form symmetry. Well, let me fix it. So if I do that, this shift is canceled by that shift. Good, I fixed it. So let me fix here too. Let me just write square because there are two number of them. So again, this is invariant. So now this theory does have one form symmetry, okay, and does not have an extra degree of freedom. Now, the only thing I need to make sure is that instant spectrum coming from this expression indeed is fractional. Okay, so let me do that exercise. Any questions?
So maybe very nice questions.
Yes.
So such kind of relations, which is divided by the n,
Yes.
is, as far as I know, it is a globally property of the group.
That's right.
Instead of the real algebra.
Yes, right.
It's widely used as physics
That's right.
instruction.
Yes.
So, as far as I know, there's no distinction between this.
Good question. Right. So, as you said, this theory locally look the same.
Yeah.
Okay. If you look at the correlation functions, local operators, they will look the same. The difference comes from the global structures, as you said. And one of the key property of global structure, in other words, one of the observable that senses global structure, different global structure, is Hooft flux. But then Hooft anomaly knows about the Hooft flux. So if you had a different global structures, you can have a different set of Hooft anomalies. And if you have a more refined, meaning instead of just the 1, 2, 3, 4, you insert extra order of n extra Hooft fluxes, you can have an enlarged set of Hooft anomalies, and that will allow you. So therefore, in other words, simply put, yes, you're right. Locally, those two theories are the same, but globally, including Hooft anomalies, can be different.
Usually one form or two forms of such kind of things are defined as a representation of Lie algebra instead of Lie group.
Yeah. So Lie algebra is the same. Sorry.
Lie algebra is the same. So because of that, I
Yeah.
think that we cannot distinguish the two cases.
Locally, but globally you can. That's what I'm saying. Yes. Hooft anomaly senses the global structures. And in fact, usually in the literature, what people call, I will momentarily introduce anomaly coming from non-trivial 1/n fluxes. That is known as not just the zero form anomaly. That is actually called the mixed zero form, one form anomaly. Okay, so anyway, so I will get there. Let's see. Okay, so let me work it out this thing. At least I thought that this is a nice exercise to show, oh, there's such a thing. If you don't get anything the rest, but at least this is a nice exercise. So let me just show that. So theta term. Okay. So this is U1. This is our UN. Okay, so let me start from here. So I just rewrote this expression. So I'm just gonna show this is fractional instanton. So this one, if you expand, includes several terms. So let me first expand the first. So that is and trace. Okay. And then the cross term, there are a number of them. Okay. Has well, I'm keep writing from this. Two and two number of them. And then there is this guy, which is plus, oh, sorry, this should be minus, plus n, because I tracing over n, identity operator gives me n, v2h. Now, because of this constraint, trace over that thing is equal to trace over that thing. Okay? So that means that this first factor is equal to n times v2. Okay. So and then so then let me just massage. So let me subtract just for the sake of it, which I will explain why I'm doing this. And I subtract it, so I have to add. So why did I subtract? Because this one alone is that of UN, but if I subtract trace part, this becomes instanton number, well, there's I theta, instanton number of SUN theory. Okay, so there's a usual SUN part because I've subtracted the trace part. Now let me work it out this part. Like I said, this is n times v2, so this whole term is n squared times v2h v2. So therefore, what I get is the I theta n of SUN, and then there was a minus n and n squared, so I get n squared minus n, okay, and then v2 h v2 over 8 pi squared. Okay, so far I just did the algebra for you, if you trust me.
Is your action real value or is it a complex?
This is complex. This is theta term. Theta term comes with I. So e to the I and theta, that kind of form. So theta is an angular variable.
Okay.
Yeah.
Then theta can have an imaginary part.
Theta is a real parameter. Yes. Usually in the SUSY, you package this theta term with the gauge coupling to make a complex kinetic function. But here I'm just splitting because I'm working in the non-SUSY case. All right, so now this relation, on the other hand, imposes interesting relationship. Because if you work this out, this relationship gives you the A1, which comes from, sorry, this dA1, the trace of this guy is U1 factor, this U1. So that gives me BA1 is equal to n times B2. So this is integer valued flux. That means that B2 has a fractional flux. Okay. Again, BA1 is regular U1. It is integer valued flux. That means B2 divided by n has a fractional one. So I can just rewrite this a little bit by making n times. Now this has an integer valued flux, so I have to divide it by n squared. So this can be rewritten as therefore n minus 1 over 2n, which I'll explain. And then let me call, I write omega 2, where omega 2 is nothing but n times b2 over 2 pi, okay, in the usual unit. So now this expression shows clearly that when I introduce the extra one-form symmetry, the instant of flux, in addition to just the integer valued flux, has an extra 1 over n valued flux. You might say, isn't it 1 over 2n? But technically, on spin manifold, where there's a fermionic well defined, this is even value. So this is 2 is gone, so it's always 1 over n valued. So therefore, instant of spectrum changed from 1, 2, 3, 4. There's a 1 over n, 1 over 2, etc. So there's a much more refined set of instantons now. And this will give rise to extra Hooft anomalies. Okay. Good. So that's the fractional instanton part. So this normally will be 20% of my talk. Now, let me be strategic. Any questions, by the way?
One question. Here you assume the existence of a one form and a two form.
Yeah.
How do we know that it exists or when it exists?
Good. So very good. Indeed, the way I present it is as if I had to assume to make this happen. But it is possible that if you're given a theory, okay, with SUN, with the matter contents, you can already figure out the electric, what's called electric one-form symmetry and magnetic one-form symmetry of that theory to begin with. Okay, so I didn't present that way, but there's a way to figure out the one-form or a higher form symmetry of a given theory right away. Once you know those things, you can just turn on the background gauge field of those higher form symmetries. Once you do that, you should get the exact same answer. So I just presented it in a more pedagogical way, but maybe it's not pedagogical because you had this question, but there's an equivalent way of doing it without assuming existence of symmetry, but rather figuring out the symmetry to begin with.
I guess my real question is the Zn you have in here related to the discrete symmetries in the anomalies you introduced beforehand?
Not yet. But,
not yet, okay.
Yeah, it's related, very deeply related. Okay, so now let me just say that, state that effect. Okay, since you mentioned, let me say that. So this theory, like I said, there is a global symmetries which had some SU and psi, etc. And then I said that there is a ZR, right? So these are global symmetries. Now, if I look at the Hooft anomaly of ZR, for example, with what? For example, I can look at the SU and psi, SU and psi. Or even I can look at this ZR with what's called the color center, like in this case 2 actually, color center. I can look at it. Now, non-trivial Zn, or in this case Z2 color center is possible only if you actually activate the one-form symmetry fluxes. If you didn't have done that, if you haven't done that, the only thing you have is just integer value of the flux. There's no fractional. So the fact that I can even ask those kind of anomalies, Hooft anomalies, is possible only if you also activate fractional instantons. So here too, if I don't activate the center, right? If I don't activate any fractional center here, the only possible instant of spectrum is integer valued. However, you can also activate the Z and psi center, just like the way I described. So by activating more, even though this is a global symmetry, you can have a refined version of a Hooft anomalies. Okay? If you have more anomalies, then you're responsible in the IR. You have a question?
So if I'm understanding correctly, so the SUN psi and SUN chi are the global symmetries. They don't get gauged at any point, right?
Yeah, no.
And without the assumed one form and two form symmetries, there's no Hooft anomalies coming from these kind of diagrams.
Yeah.
Right.
Yeah. So good. So that what you said is correct.
Okay.
Therefore, really, I didn't even explain CFU anomaly. So the concept of CFU anomaly is that even more general version of what I just described. So the game is the following. There is a center symmetry of color, okay, which I don't even know exactly whether it's 4 or 2 a priori. There is a center of a flavor symmetry part, okay? And then there is another center of a chi flavor symmetry. And there is also a center of a U1 exosymmetry. What we have shown is that if you look at the individually, you might figure out how much flux you can turn on. But what's interesting is that sometimes, even if you look at one factor, you might say, oh, there is no fractional instant you can turn on. It is possible to turn on in a more collective manner so that the problems are canceled out. So it is possible to turn on fractional in such a way that the combination, as a combination, is consistent. So that's called the solving cocycle conditions in constructing the bundle, but that's possible. So what we have, therefore, the reason why we call the CFU flux color non-abelian flavor and U1 is that there is a color non-abelian flavor and U1 center you can turn on simultaneously, but it's not randomly turning on. They have to satisfy very, very precise conditions. Once you do that, you can turn on a set of fractional instantons simultaneously. Then all of a sudden you have a much more refined Hooft anomalies because of that. Okay, so that's the CFU anomaly story. Okay, so given the time, now let me state the result. Well, to be honest, anyway, so any questions before I move on to the next thing?
One big question.
Yeah.
So this B2 is not dynamic of field.
Good. So this is background gauge field for now. That's right. Yes. In fact, okay, let me just say, as a quiz, this action is otherwise known as the Zn topological field theory, and the other name for this particular action is called the BF theory. Maybe I said that during my Jeju workshop thing. So therefore, in the literature, one interpretation of this vision I'm just telling you is that take SUN gauge theory, couple that to Zn topological field theory, and that coupling turns instant spectrum from integer value to 1 over n value, fractional value. So that's the one of the TQFT part, but there's a more important TQFT part. So I don't have time to list all the Hooft anomalies. My note has very detailed, but there's that. So, but then let me now mention at least one very important thing, because I didn't even get the bosonic part. So let me mention very quickly this part. And then I will mention a couple of Hooft anomalies, matching business. So what is the bosonic part? And why it is important? Okay, it will turn out to be extremely important. So let's see if we can construct a fermionic operator. Bosonic means the theory doesn't admit any fermionic gauge invariant operators, right? So that's what it means to be bosonic theory. Okay, everything you see is a bosonic state. So let's try to construct the fermionic operator and see when we fail. Okay. So the general form of fermionic operator will look like some number of insertion of epsilon, the epsilon tensor, like epsilon here is I1 to the IN, that tensor. Some insertion of psi, some insertion of chi, and sometimes you need to also insert some number of color field strength tensor. But let me drop this for now, because it's not important. Now, first, gauge invariant means that, so this one has a 2 up index, this one has a 2 n minus 2 index, this one has a n down index. So that means that 2b plus n minus 2c should be equal to 2a. So that's the contraction of all gauge indices, right? So gauge invariance means that this needs to be fulfilled. The fact that I want to construct the fermionic operator means the number of fermions, in this case b plus c, should be odd number. K is integer. Okay? Now, you can try to solve this thing. For example, let's get rid of B in this equation. So what do I get? 2 times 2K plus 1, I'm just solving this, minus C, n minus 2C equal to 2A. Okay, good. So that means that the 4K plus 2, let me absorb, n minus 4C is equal to 2A. So now let's consider when n is equal to 4 times integer. So let me call 4L. Okay, so now I consider example that the number of color is 4 times integer. Okay, so what that happens is that then let me divide it by 2. Okay, good. So if you divide it by 2, then you can see that, A. No, this is n, right? N times A. Okay, this is n times A. This is n times A. Okay, good. Now you can show that in this case, there is no solution to this equation. One way to see that is that, so this is also for L. Okay, so there is 2, and you remove you see the rest is the 4 times something. Okay, divided by 2, you get 2 times something is equal to 1. Obviously, there is no solution to this equation, right? So that means that when the number of color is 2L, for L in this case, there's still fermionic operator. The theory becomes completely bosonic. Okay, that's first step. And in the list of the theories I said here, in case you can just take a look at the whiteboard, the only case which are not bosonic is therefore 5, 6, 10. The rest is all bosonic theories. Now, let me just say quickly why it is important to be bosonic in this example. That's because of the Hooft anomaly matching. So let me just move on to that. So in the remaining, let's say, can I take like 7 more minutes? Yes. Nominally, okay. So this will turn out to be very, very important basically now. Okay, so let me talk about Hooft anomaly matching. Anomaly matching. So there are 4 different kind of symmetries we can talk about. One, so let's imagine now that the theory may confine. We want to check whether theory can confine. So let's say theory may confine. There's some vacuum operator, vacuum condensate, which will lead to some particular pattern of chiral symmetry breaking. So I'm imagining there's some sort of now confinement with a vacuum operator. Now, there are 4 different kinds of symmetry I can talk about. 1, unbroken continuous symmetry. Okay. 2, there might be a broken by condensate continuous symmetry. 3, there can be unbroken discrete symmetry. 4, there can be broken discrete symmetry, right? So there are continuous and then discrete, and then it can be either broken or unbroken. How do we match anomaly associated with each of these symmetries? So for unbroken continuous symmetry, there is a theorem called Coleman-Grossman theorem, beautiful theorem actually. It is derived not by field theory, but in terms of S-metrics language. It's a beautiful paper, saying that such anomaly must be cancelled by massless. So there's a gatless spin half state, meaning fermion. Okay? You don't have an option, but this is the only way you can match the anomaly. At this moment, you might say, boom, something happened, right? Because I said our theory is bosonic. First of all, and if we had a global symmetry like this. So if vacuum condensate does not break such a non-abelian global symmetry, even including U1, to anomaly-free global symmetry, somehow we are in trouble because there is no way to match unbroken continuous anomaly. So this puts a first constraint on the possible vacuum condensate, right? Given a global symmetry, continuous symmetry, vacuum condensate, there's a space of vacuum condensate I can list, enumerate. And out of that, only the ones that can successfully break this down to anomaly-free subgroup that can survive. Is that clear? Because I can't leak out any anomaly from the continuous symmetry because they can only be matched by massless fermion. But our theory does not have massless fermion. That's constraint number 1. Constraint number 2. Broken continuous symmetry can always be matched by another gapless mode called the Goldstone boson in terms of Weissmuller-Witten term. So that can be done. That's why I said that we should break because it is guaranteed to be matched by Weissmuller-Witten term. Third, unbroken discrete symmetry is problematic. So this can be matched either by gapless or massless fermion or by breaking, like continuous symmetry, by breaking, or what's called symmetry preserving TQFT. Because the discrete symmetry in nature is discrete, in addition to the gapless fermion, there is one extra way to match those such anomalies. Okay? Now, again, this option is gone, right? So if we had anomaly for this discrete symmetry, okay, or we had a U1 axial, let's say it is broken by vacuum condensate to some discrete symmetry ZQ, here too. If there is an anomaly leaked out in the IR from any of these anomalies, the only way that those can be matched is by something called the symmetry preserving TQFT. Now, looks like very fancy name. Now the question is, can we have such TQFT in the IR, right? And there are 2 theorems proposed 2019, 2020, very recently. There are 2 theorems. And before that, there was a work by Witten, and after that, there was a Zubin, Wang, Wen, Witten paper, and then more recently, there's Clay, Cordova, and Kantaro Mori papers. It's not a whole set of theorems. There are 2 theorems when you can or cannot have such a symmetry preserving TQFT to match anomalies. Okay, so the bottom line, we have checked that whenever there's a leakage of anomaly from unbroken discrete subgroup, there's no such TQFT. That means that I cannot possibly allow a vacuum operator which leaves out any unbroken part of the symmetry, the discrete symmetry with the anomaly. Okay, so that puts another very strong constraint. Hopefully that explains. I hope to be able to explain you better, but I don't have time. That's the TQFT part, very important part. Lastly, broken discrete symmetry can be matched by anomaly for discrete symmetry can be matched by just like this. There is a version of that called the domain wall. Or we have shown that there is a for more general discrete symmetries, there is a universal TQFT that matches anomalies. So this is easy to do. This is easy to do. The trouble is whenever you have unbroken symmetry, that's what puts a constraint on the possible vacuum operators. Okay. Now let me answer. That might be the last thing I want to say.
Could you explain the first one again?
First one.
Yeah.
Yes.
The unbroken continuous symmetries have to be anomalies?
No. So whenever I say this, I assume if there is some anomaly associated with those symmetries, those anomalies, for example, matched by the corresponding thing here. So if you have unbroken continuous symmetry who has Hooft anomaly, that anomaly can only be matched by massless fermion, which cannot be done in this theory.
Right.
Therefore, I cannot have continuous symmetry unbroken with anomaly in the IR.
Yeah.
That means this vacuum, which does the job of breaking continuous symmetry and discrete symmetry, should be special.
Yeah.
Such that it breaks any global symmetry, continuous symmetry down to the only anomaly-free subgroup. Because then I don't have to match anomaly because there's no anomaly there. Okay? Is that clear?
Yeah, that makes sense.
Same applies to the discrete symmetry too because of these TQFT theorems. Now, let me just now list a couple of expressions explaining how strong constraint we can possibly get out of this exercise. So that will be my more or less last two I can say about it. Good. So, for example, if we take the SU8 gauge theory, with one number of psi symmetric and 3 number of chi, so conjugate of antisymmetric, just from these 2 to 4 conditions. We didn't even include the first condition. Just from the 2 to 4 conditions, what we can show is that the allowed vacuum operator are the following list. So I'll explain. Okay, so just from the 2 to 4, we can rule out everything but this list. There's some higher dimensional thing going on. However, the lowest dimensional one, which is a fermion bilinear, so in more detail, this means that there's I1, I epsilon to 8, like I1, I2, chi, I3, I whatever j, and there's a one field strength should be contracted here, j is something like that. Okay, so there's that kind of dimension 3, 5 operator. So the lowest dimensional operator has a dimension 5, but it is easy to show that this is ruled out because of the first constraint. So one can check what are the unbroken continuous symmetry. The thing is that there is unbroken U1 symmetry, and then there's a Z2 symmetry. Both of them has a Hooft anomaly. Like I said, if you have a continuous symmetry with anomaly, it must be matched by fermion. There is no fermion, it's dead. If there is a Z2 or discrete symmetry with the anomaly, unbroken discrete, it must be matched by symmetry preserving TQFT. We show that there is no such a thing, so it is ruled out. Now, the next available condensate you can look at from this list is that this is the lowest dimension possible without even including this constraint. Okay, now let's count the number of dimensions. This doesn't even include the number of possible insertions you need to do. So because of the Fermi statistics and symmetry regions, sometimes you have to insert some number of f's, which is something like that, okay? So let's look at the dimensions. So 3/2, this is 26, and plus possible dimensions of these guys, okay? This is what? 39 plus extra. Okay? Once again, this doesn't include possible conditions from this, which you have to, work it out, the group theory of contractions of 26 indices. Crazy level. But let me be generous saying, okay, yes, let's say I pass you for the continuous thing. Even then, this start with the dimension 40 operator. And then you run down to the EIR. Somehow this guy should survive. How? Like you have to pick up enormous size of the negative anomalous dimension to survive, and then condensate. If you ask the same question, even worse. So this suggests to us that this theory doesn't quite want to confine. See, there's a very strong constraint from this, the non-perturbative analysis. And the best shot is that A, yes, someone magically pick up very large negative anomalous dimension, survive, boom, happens, only if we satisfy these first conditions. Or it can go to somewhat exotic phase, like exotic Coulomb phase, like there's an asymptotic free theory, and the strongly coupled theory itself breaks its own gauge symmetry down to the IR free gauge group, so it becomes a freer in the IR. Such a thing is possible, has not been demonstrated in the 40 non-supersymmetric gauge theory yet, nonetheless logically possible. Therefore, we conclude that the most likely scenario is that this theory may want to go to the IR infrared fixed point, just the conformal field theory. And then one can check perturbatively whether this theory actually do admit perturbative fixed point. It does. So at 3-loop level, it does admit fixed point. The coupling is a slightly bigger than you might have hoped to be perturbative. Nonetheless, it does have the fixed point. And maybe actually runs to the slightly strongly coupled fixed point. And then we have checked the same theory and double the matter contents like that. Again, we did the same analysis. There's a similar patterns. In this case, lowest dimensional operator has a 12 fermions instead of this. And there, it does admit actually perturbative fixed point. So just from the non-perturbative analysis of our work and check from the perturbative fixed point, suggest both that theory actually wants to go to the infrared fixed point rather than confining. Okay, so hopefully I conveyed you a message that there's a new anomaly which didn't have a lot of time, but from a CFU fluxes we can get much more anomalies. And then using the TQFT theorems, we put a constraint of possibility of confinement because theory is bosonic, ruling out a lot of possibility from the first kind. Okay, with that, thanks for your attention and sorry for running over time.
Thank you for the very nice talk. Any questions?
Yes.
By fixed point, you mean one like fast?
Correct. That's right. So we use the both 2-loop and 3-loop beta function equations, and then check whether there's there's a fixed point, B, what's the size of the gauge coupling at the fixed point. In the first kind of theory, there is a fixed point at 3-loop, but not at the 2-loop. The size of the fixed point coupling alpha, which is square of 4 pi, is like 2 point something. So it's a little bit large to believe the analysis. Second kind, we check both at 2-loop and 3-loop level. We do have a fixed point. The size of the coupling is like 0.3 or 0.1. It's very perturbative. So combining with the both analysis, we really somewhat confident about this second theory, for example, that it will actually go to the fixed point rather than being confined. Yes.
If you only consider one loop level for the beta function, what is it? What?
Oh, good. So in order to actually check the fixed point, you need to have at least a 2-loop because so d alpha dt, this is log mu. There is a beta 0 g squared something minus in the beta 1 g to the 4. So at least you need to have two to balance again to set it to the 0. Okay, so that's why I didn't mention one loop. Either you have to have at least two loop or 3 loop to check.
Just to understand, you demand the bosonic theory in order to get the additional conditions 1 and 3, right?
Basically only 1. 3 always the 3 doesn't require the bosonic theory.
Okay.
Actually.
Yeah. So you could do the same analysis without condition 1, even for the fermionic theories.
So can you
conditions 2 to 4, you can still check even in fermionic theories, right?
Correct. Yes.
And another question I had, you demonstrated the whole construction here for SUN gauge theories.
Yeah.
Is there any principal point stopping you to do this for SP2N or SON gauge theories?
Yeah, you can play the same game with the SO, SP, or any kind of gauge group. That there is no limitation. Although if you go up very high, like some exotic gauge group doesn't have a fractional instantons in it, but nonetheless, since I made use of a fractional instanton from flavor symmetry group part 2, there's still room to play out. But definitely SO, SP, I'm sure people work it out to see.
I see. Has been work done along those lines yet?
No, to my mind, the fact that the importance of bosonic and the usage of a TQFT theorem, I think our work is really the first.
I see. Thank you.
Yeah, thanks. Thanks for the questions.
Other questions? Other question in Zoom?
What happens for the supersymmetry?
Oh, good. So in principle, if you go to the SUSY, you get a stronger, tighter game. So even with that, so good. So I'm not aware of a SUSY works with the bosonic thing make use of it heavily. Okay, all the cyber duality I know of doesn't really make use of this. However, I believe that there's room to improve SUSY analysis too. So for example, Yuji Tachikawa and his group in Japan, for example, improved the Cyberg SO dualities, pointing out that there's an extra TQFT you have to introduce to restore the consistency of the analysis, for example. So there's that extra direction to go. But like this line of analysis, I don't know of, again, any SUSY analysis, but I'm sure there will be something interesting to be find out.
So the choice of fermions was specifically to get the bosonic?
Not really. So we begin with this. Good. So good. First of all, as you might see now, because of the analytic, meaning number of boxes here, we have extra one form color center we can turn on. That's A. But this is not necessarily just because of bosonic. B, the same theory, for example, the first one, was studied earlier by some groups, people you may know if I say the name. They missed these new anomalies, for example, because they only turn on the center flux, color center flux, and they see whether there's extra anomalies. They couldn't find, which we reproduced it. Only if you turn on full CFU fluxes, very refined version, then you get extra thing, and then you get extra constraint on the possible vacuum. And then nobody, I think, actually try to look into the entire space of vacuum operators. People just, for example, consider this and analyze what happened. But here we just say, what will be the all possible vacuum operator to begin with? Therefore, we have a global picture of the status of confinement altogether.
But the proof that there's no fermionic operator relies on the number of indices.
Good, yes. This relies on the particular representation. And then one can show that QCD-like theory in principle can also be made to be bosonic too. So there's also room to play out what happened to those QCD-like theory if it becomes bosonic, because then you get a very strong constraint from the first kind. Yeah.
One clarification. I mean, about the higher form symmetry.
Yes.
Also, there is some higher form symmetry of space-time symmetry.
Oh, very good. Yes, the answer is yes. Good. So for example, in SU2 gauge theory, there is a paper by Clay and Thomas Dumicurescu, 100 pages long, but extremely useful and then very pedagogical paper. They are, for example, you can put, good. So if you put theory on what's called the spin manifold, which I focused today, there's no one form flux, like two form flux of the space and time. But on the space-time manifold called non-spin manifold, which means that naively, so space-time manifold they ask for, I'm talking about Euclidean signature, okay? So of course we have to talk about 3,1, but I'm just talking about SO4. And SO4 group doesn't admit the fermions, right? As you know, you have the double cover. And that double cover is SP4. Spin 4, sorry. I didn't mean SP. Spin 4. But this uplift or double cover is not always possible. When this is possible, you call the space-time manifold to be spin manifold, because spin. Okay, when this is not possible, you figure out whether there's other ways of doing that. But the fact that sometimes you cannot do that, but sometimes you can, even though naively you cannot do by the help from the other global symmetry sectors. In this case, you turn on the Z2 center from this. So there's a what's called the state of Whitney class from this sector. And then you also turn on from this sector, there's a Z2. This double covers Z2. And then you make a correlation between these two such that even though you cannot do the uplift alone, from the help from the other global symmetry sector, sometimes you can do that. Okay? Those construction is known. And we also have done this. Our CFU flux all include all this kind of thing because we are supposed to be most general, most refined fluxes. Yeah, so my answer to your question is that sometimes you do have a two-form background field. That means that there's associated the one form with it, but not super naive.
Any other question? So if not, let's thank speaker again. Thank you very much.
Thank you.